Hi, in this video, I would like to share with you a table I designed to help us get a big picture of the condensed state of molecules. So I know that some of this print might be a little hard to read, but I'll try to zoom in whenever I can on the video. So let's take a look at the top. Your very first thing you're going to be doing is identifying the elements present. And there are four main types. There's others, but I'm going to be looking at network covalent, metallic, ionic, molecular covalent. I'm not really looking at, for example, coordinate covalent. Okay, so the very first thing you want to do whenever you're comparing substances is ask yourself, is it network covalent, metallic, ionic, or molecular covalent bonding? Now, if it's network covalent, it's a long-range array of covalent bonds. You can still use VSEPR, valence bond theory, hybridization, when you are dealing with network covalent. But the key thing here is when you are dealing with network covalent, you are actually breaking covalent bonds between atoms. And that takes a lot of energy to do. So these have very, very high melting points. If you can keep in your mind some penultimate examples of these, it can help you understand the properties. So diamond, just think how hard diamonds are. Sand and glass or silicon dioxide or silicates, they're much higher melting points typically. And so you don't have to memorize that range, but I like to put that into this for comparative purposes. If you're talking about metallic bonding, what we're looking at is electrostatic attractions between ions and delocalized. I think that's an important word. Delocalized valence electrons. They're not fixed to a location between two atoms. You have a sea of electrons that are free to move. Now, these bonds are also very strong. A range I found of anywhere from 50 to 1,000. So you want to think of pure metals. Some of them are soft with low melting points, like mercury, for example, but some of them are very, very hard, like, say, titanium. So if you can think of, some pure metals like, titanium, iron, copper, so forth, or metal alloys like brass or bronze. Alloys are mixtures of metals that have metallic bonding. That might help you understand. Then we have ionic bonding, electrostatic attraction between cations and anions. And what we have is a very fixed, rigid structure as solids or in the very condensed state, alternating positive, negative, no movement of electrons when they're in the solid state. So to break those force of attractions, I'm actually having to break a bond between two atoms. And that takes a lot of energy to break. So think sodium chloride. Okay, would be a good example of this. All right, sodium chloride, high melting point. All right, and then we get into molecular covalent. These, if you look at the range of energy, we're talking about much orders of magnitude less energy to break the forces of attraction between molecular covalent molecules. And that's because we're talking about an attraction between neighboring molecules. It is not a bond. If you use the word bond, you will lose credit. We're talking about attractions between discrete molecules. And we use the types of models like VSEPR, valence shell electron pair repulsion, hybridization. Of course, at higher level, you would be getting into a molecular orbital theory and that type of thing. All right, so once in this case you've identified as molecular covalent, next you have to define whether it's polar covalent or nonpolar covalent. If it is nonpolar covalent, the force of attraction that you're breaking is a London dispersion. London dispersion is a temporary intermolecular force, a temporary dipole-dipole. It is so small that even though it occurs in ionic, metallic, and network covalent, it doesn't even enter the conversation. It just will never be a real contributing force. We will always approximate it as zero and not really talk about it. If it's polar covalent, you know right away it has London dispersion. So I would write, if it was polar covalent, I would write LD right away. Polar covalent has London dispersion. But it also has a dipole-dipole. And within a given molecule or between same size, dipole-dipoles are stronger. Okay, so I'd ask myself, is it nonpolar covalent or polar covalent? If it's polar covalent, I put down LD-DD. And then I ask myself one more question. Do I have an H bonded to an N, an O, or an F directly? And if the answer to that is yes, I also have hydrogen bonding on top of the London dispersion, dipole-dipole, and now I would add hydrogen bonding to that. So some examples. For pure London dispersion, anything that is just carbons and hydrogens is considered to be non-polar and would have a dipole-dipole only. Polar molecules, HCl, H2S, NF3, any of those polar molecules, SO2, those polar molecules would have a dipole-dipole. Prominent examples for hydrogen bonding are going to be water, ammonia, NH3, alcohols. Alcohols have, I don't have a lot of room, I hope you can see this, alcohols have OH groups in it. Acids have C double bond OH, even more or stronger hydrogen bonding. Sugars have a lot of hydrogen bonding, which is why sugar is so soluble in water because of that hydrogen bonding interaction. Okay, now I'm talking in this case, there's a little caveat here that London dispersion is smaller, assuming same size. In another video, I talk about the effect of increasing size on London dispersion. You may want to check out my intermolecular forces and potential energy video. Thanks for joining me for this one as I try to give you a flowchart approach to comparing types of substances. Thanks for joining me.